So the Chinese writing system is incredibly rich and has an enormous history behind it. The writing system was developed well over 4,000 years ago, and the original symbols really were pictures representing objects or things. Over time, the ideographs became sort of stylized, and some are reminiscent of the original sort of pictographs, and some have diverged quite a bit. The Given the history of the region, that writing system has been adopted not just by China but other countries in the region. So you have China, which refers to the characters as Hanzi. You have Japan, which uses kanji, which is really using the same ideographs for basically different language. In Korean, you have Hanja, similarly using Chinese ideographs to represent Korean words. And Vietnamese, traditional Vietnamese also uses Chinese characters. The challenge of ideographs is that they're incredibly complex. You've got quite a number of strokes that make up some of the characters. The record for strokes is the word Huang, which I think in this case is just the name, but it has 172 characters. It's very common to find, 172 strokes. It's common to find characters with 60 or 70 strokes. And the characters represent quite a rich set of not just words, but tones. Chinese is a very tonal language, and there are different sort of inflections for the same syllable. When rendering the Chinese ideographs into, say, Latin characters, you add tonal marks to represent how the syllables should actually be said. Japanese is not as tonal, and so to take the ideographs and have them represent Japanese, you would not actually, when romanizing or Latin, transliterating to Latin characters, create tonal marks because that wouldn't be as appropriate. So it's important when looking at a string of Chinese ideographs to know, is it really referring to Chinese? Is it really referring to Japanese or Korean? Because we want to know how the word represented by the character should be rendered. Transliteration is a unique challenge because you're going from not just a different language, but also just a completely different set of writing to typically to a Latin language or Latin character-based language, as in English or the Romance languages. And when doing so, we have to differentiate between transliteration and translation. So very commonly, we think of, let's say, transliteration. So how to represent, say, foreign words in, say, English, and typically to get the pronunciation right. But there is also translation. So, for example, the country that we in English call Italy, in Italian, it's Italia. And the capital of that country we would call Rome, but in Italian, it's Roma. So really, we could keep the name Italia and Roma and represent the sounds, say in English. That would be transliteration. But really, what we do in English is in that particular case, we're doing a kind of translation, which is we are calling the country Italy and the capital Rome. So when we look at, say, Chinese, if we look at the capital of China, we call it Beijing because there we're doing a transliteration. We're trying to represent the sounds as a Chinese speaker would say it. We're not thinking so much about translation because the quite literal translation of Beijing would be northern capital. But we want to preserve the pronunciation. Now, as I mentioned in an earlier question, we have to think about different concepts like the tonal marks. So if we wanted to transliterate the Chinese ideographs very well, we would use a system like Pinyin, where in Chinese ideographs, Chinese sounds get written as Latin characters, but also that there are tonal marks. So that way we can actually try to imitate as well as we can, not just the sound of the syllable, but the tone of the syllable. It's important to know that if we're dealing with, say, Japanese or Korean, which can use Chinese characters, the tonal marks would be very different. And in Japanese, tone is not as important. So rendering it into Latin characters, you generally don't have tonal marks. So knowing the language represented by the ideographs is important, and how to preserve the tonal marks is very important too. So fuzzy name matching is a process by comparing two names and in a fault-tolerant way assess if the two names match or not. And a very simple example, my daughter's name is Sophia. And you'll commonly see Sophia written with a PH, so Sophia. And another common way of writing Sophia is Sofia. Neither one is right or wrong. Sophia has a Greek origin. And these are just different ways of representing the original Greek name. So a person may have a particular spelling of the name. My daughter's name particularly is Sophia. But one can imagine that if she goes to, let's say, a customer service desk and they need to write her name, they might hear the name and write it as an F. And so then the question is, did they get the name wrong or not? Well, they got the name wrong in the sense that that's not the name on our birth certificate, but it is a valid rendering of the name. And so if we wanted to look up that name on a, let's say, some customer record, we want to be able to match the Sophia with an F with a Sophia with a PH so that we could find the record that we're looking for. And fuzzy name matching does basically that. Now, how is that important for dealing with non-Latin languages? Well, there are many ways of writing names that occur in non-Latin languages, non-Latin scripts. So imagine a common Chinese name like Wu. Is it W-U or is it W-O-O? Well, there are different standards for transliterating the same sounds. And so it really could be either. It also could depend on what the original script was. And so that would tell us how the more correct transliteration should be. This becomes a lot harder in languages that really don't have vowels. So for example, in Arabic, the name Muhammad very commonly gets rendered into English as Mohammed with an M-O or Muhammad with an M-U. And really both are correct because Arabic essentially does not have vowels. And so the vowels are really kind of filling in the way a non-Latin speaker would say it. So fuzzy name matching really tries to address these problems by being fault tolerant, being aware of the transliteration standards, what are valid transliterations, what are not, and ultimately try to determine, do two names match each other, or are they effectively not a match? Pairwise name matching is an application of fuzzy name matching. So fuzzy name matching is a set of algorithms. Those algorithms are applied to names to find out, do names match? But really, it's a very general set of algorithms to, in many cases, look up names against a list. Pairwise name matching really means I've got two names and I want to do that comparison. So in a different question, I gave the example of Sophia with a PH and Sophia with an F. We can imagine that I looked up Sophia with an F on a customer list, and Sophia with a PH came back. And I might say that's an acceptable alternate spelling of the word. So pairwise matching is really going to say, I've got the two names. And this is important because imagine I've got an existing system, and that system already I query names and I get an answer back. I can use pairwise name matching to be a sanity check on that system and say, does my pairwise name matching system agree with what the established system, the in place existing system, does it? Do I agree with the answer it's giving me back? And this, how does it help Chinese names, which is really the topic we want to talk about? It's important because we can use this and all the knowledge we have in our system for how to transliterate Chinese, how to smartly and in a fault-tolerant way do those transliterations, and ultimately look at an existing system and do that sanity check on it and say, did we find the correct Mr. Wu, to use the example I just mentioned? Is the, to use another example, the name Yang, is it Y-O-N-G or Y-A-N-G? And the system that is in place and is returning an answer, does the fuzzy system, the fuzzy name matching system, really agree with it? With pairwise name matching, we don't have to rip out into the other system. We can use the pairwise name matching as a sanity check. The name matching system by Babel Street and incorporated into IMTF employs a two-pass system. And what that means is we are trying to address the issue of precision and recall. So in the general system of identifying records, matching names, resolving identities, you've got two challenges. You need sort of think of it as breadth and depth, right? How many names are we looking at when we're considering candidates? And then how precise are we when we consider those candidates? So how wide is our search? And then how accurate is our search? So how wide is our search is really a recall problem. And how precise is how accurate is our search is a precision problem. And different systems really try to optimize one over the other. With our two-pass approach, we really are trying to do both. And so when we receive a name, we encode that name in a variety of different ways. But one of those ways is to make basically a hashing function and to create a hash of the name, and basically to create a set of keys that represent that name. And so when we try to look up that name, we try to find all the names where the keys match, those names become the candidates because their hashes match the name being queried. That is our first pass. That's our recall pass. What is the breadth of the search for which there's a likely candidate? Somewhere in that set of names whose keys match, we have a likely candidate for a matching name. Then, given that set of candidates, we're going to apply our AI and machine learning algorithms to see which name more accurately matches, given the challenges of transliteration, given the fault tolerance for things like misspellings and different transliteration standards. So that is our precision pass. And put the two together, and we will generate an answer that has had the widest breadth possible, but the most accurate analysis possible. And this can be done in a speedy way. When talking about how long does all of this take? Well, it can take milliseconds. And it does depend a bit on the size of the data set, on the size of the list of names being queried. But very often we can do this in sub-second response time. The algorithms that I've described in the previous questions, they are statistical models based on what's called the hidden Markov model or hidden Markov method. And that is basically, to put it in computer science terms, a finite state machine. And a finite state machine that looks at a particular character and then tries to decide what is the probability given an input character of a particular output character. And if you remember any of your science classes and you remember Greek from, let's say, school science or math, an alpha is typically an A, right? An alpha in Greek is typically maps to an A beta typically maps to a B, a gamma typically maps to a G. So one can imagine that a finite state machine, when given an alpha as an input, that machine is going to say almost all the time an alpha is going to be an A. So I'm going to see an alpha come in, I'm going to output an A. And that would be a very simple machine, right? And so one would imagine that as this little machine went down a string of characters, when it saw an A, it would emit, I'm sorry, when it saw an alpha, it would emit an A. When it saw a beta, it would emit a B. But what happens when it encounters the phi or phi character? So that typically is a pH. And there are different ways of rendering that character in English or in Latin characters. You could render it as a pH. So I gave the example in an earlier question of my daughter's name, Sophia. And you can render Sophia with a pH. You can render the phi character output a pH when you see phi as an input. But you can also render it as an F. And so then the question is, how does the Markov model know that? Well, this is machine learning, and you give it banks and banks of input names, and then it's going to know that a certain percentage of the time, when encountering a phi, a pH is emitted, but certain percentage of the time, an F is emitted. So with that, we can create this machine that goes down strings and emits, given input strings, emits output strings. But we've actually built an improvement on that because we've built a neural network. A neural network is also a kind of finite state machine. but the set of states is far deeper and richer. It still is based on probabilities, and it still learns by machine learning in the sense that it takes banks and banks of input to build the probability between the states. But as the name implies, it's a neural network. It's trying to represent the interconnections that, say, neurons have. And so you don't have just a single state. You don't have a single, oh, there's an alpha coming in, so an A goes out. You really want to look more at sequences of characters. And given those sequences, can we generate output sequences? And then given input sequence, what's the probability that a particular output sequence might be the match? And so given that, we can actually have a more accurate determination of how two strings match. In our particular case, we trained a deep learning neural model for matching katakana to English. And so in that case, we've got a katakana string and an English string or a Latin character string. And instead of going a character at a time and either admitting the English for transliteration or comparing with the English to do matching, we can take entire sets of strings. And in that, we get a far more accurate answer as to whether the English Latin character string matches the katakana. We are always working to improve the Babel Street match. And some of the areas where the improvements are coming are first with speed. No matter how much we improve name matching, people will always want it faster, and with good reason. You've got to process the input very fast. You are in environments where speed matters. If you want to do, say, processing a payment, if you want to be in a high volume environment where you're not just looking up a particular name, but you're looking up many, many names at a time, you need to have not just sub-second response, but response that's on the order of only a few milliseconds. So we've been optimizing our name matching solution to have it run as fast as possible, but we're looking to do more. And one of the things that we're looking at is running on hardware, particularly GPUs and NVIDIA GPUs. So our AI machine learning algorithms, our deep learning models, our in-Markov models, they are AI algorithms, and they lend themselves quite well to run on GPUs. And so we're looking at hardware acceleration to have name matching run as fast as possible. Another area is language support. We support about 25 languages, and we're always looking to add more. And that means a variety of things, right? So when we support a language, we don't just say, oh, we're going to see if this name of this particular language matches a name of another language. We do quite a variety of things. And so one example is we do what's called name frequency models. And so we are looking, let's say, a name like John Smith. The words John and the word Smith in a namespace are both relatively common. But imagine you had a name like John Rutherford. Well, Rutherford would be far less common than Smith. And we would want to give Rutherford more weight to the overall name score than John. And so in addition to the matching algorithms, we've got these name frequency models where we can evaluate and weight the name components. These are things that we are constantly looking to improve. So adding languages means gathering data to inform these kind of scoring algorithms. But the existing names we've got we're also looking to reevaluate that and make sure that we're doing this as accurately as possible. And that's in part because names change. Um, if you looked in some countries, Muhammad as a first name might have been rare, um, given migration, given immigration. Muhammad is more common in Western countries than it was before. So the name frequency model needs to adapt. And those things have to be basically become living models. So we're always updating our models. We also provide ways for customers to update these models on their own so that if they've got data or they're working in a jurisdiction that we don't have access to, you can have the model be as accurate as possible. So these are ways that we improve our screening, and we're always looking for more ways to improve. Let us know if you've got other ways you'd like to see the system improve.